Hello. In this video, we're going to take a look at the notes for AP Physics C, Unit 4, Momentum. Please remember to pause or rewind the video as necessary. Section 8.1, Center of Mass. The center of mass of an object is a point when an object could balance if set on a fulcrum. Think of a fulcrum as a point of rotation, like a seesaw or a teeter-totter would sit on a balance point. That balance point is called a fulcrum. Now we're going to abbreviate center of mass as CM, so be aware of that for future note-taking. The center of mass is also where all of the mass of the object could be considered as being concentrated. The center of mass of the particles is a weighted average of all the position of all the particles. The average is weighted by the mass of the particles. For a system of particles of mass m initial and mi and positions xi, the center of mass could be defined as x cm, that's the position of the center of mass, is equal to the sum of all of your mass times positions divided by the sum of all the masses involved. So let's take a look at this example. We want to calculate the center of mass and then mark it on the number line. Now we're going to make this dark line right here in the middle x equals 0 as a reference. Now you can see the points are here. This one is at -2. Let's see, 3, 4, 5. This one's at -10. This one's at 4, and this one's at 10. Just so we can establish the number line. So XCM, there are 4 masses involved here. So we're going to add up 4 masses and their positions and divide it by the sum of 4 masses. So I'm going to start with this. I'm going to call this mass 1, mass 2, mass 3, and mass 4. So we're going to go 3 kilograms times -10. I'm literally noting its actual position. Plus, the next one is 2 kilograms times -2. Plus mass 3, 1 kilogram times 4. Plus mass 4, which is 4 kilograms, times 10. And we are going to divide all of this by 3 kilograms plus 2 plus 1 plus 4. Okay, let's break this down. So the first part is going to be -30 kilograms times meters plus a -4, so -4 kilogram meters. I'll keep it as plus a negative. So plus a -4 kilogram meters plus 4 kilogram meters, right? 1 times 4 is 4. And then plus 40 kilogram meters. All of that is divided by 5, let's see, 5 plus 5, or 10 kilograms. Okay, well, this one's kind of easy. The -4 plus 4, that cancels, and -30 plus 40 would, of course, be 10 kilogram meters, and that's divided by 10 kilograms. You can see that part cancels, and then 10 divided by 10 means that the position of the center of mass of this 4-mass system would be located at 1 centimeter. I'm not sure why I wrote centimeter, meter. There's XCM right there. Example, suppose there are 6 billion people, 6 times 10 to the 9 would be 6 billion people on the earth, all of whom are in the state of Connecticut. So that would be quite a population density there, so that each person has 1 square meter of area to him or herself. And that person has an average mass of 100 kilograms. If everyone jumps 1 meter into the air at the same time, the Earth itself, of course, has a mass of 6 times 10 to the 24, and a width of a carbon atom is 1 angstrom, or 1 times 10 to the negative 10 meters. When the people jump, what doesn't move is the Earth people center of mass. So the concept is basically this. In the absence of a net force, so when the people jump, they apply a force on the Earth applies a force back on the people that are jumping. There's no external forces acting on the system other than that. Therefore, a couple things happen. 1, energy is conserved. 2, momentum is conserved. And 3, the position of the center of mass is conserved. It stays the same place. So it's not going to move. The position of the center of mass is not going to move. So how far will the Earth move when all the people jump? Well, we can kind of establish a bit of a ratio here. If the center of mass does not move, so the center of mass we can describe it as mass of the Earth times mass of the people, the position of the people. Well, let's go ahead and solve this for the distance the Earth moves. Well, the mass of the people, we have 100 kilograms times the fact that there are 6 billion of us, okay, times the position of the people, the distance the people on average are moving about 1 meter, jumping 1 meter upward, and compare that to the mass of the Earth, 6 times 10 to the 24. And so what we get with this, that all cancels, and that gives you 100 times 10 to the 9 over 1 times 10 to the 24. Put that in your calculator, and the Earth would budge about 1 times 10 to the negative 13th meter, which is pretty small. Let me see. 1 times 10 to the negative 13. So that would be 12. So it would be 0.1 picometer, which is the same as 1. So it would be negative 12, negative 10, negative 9. It would be 0.001 nanometers would be how far it actually moves. Section 8.3, velocity and the acceleration of center of mass. The velocity of the center of mass is the rate at which the center of mass changes. So in other words, we can take the derivative of the position. And that should make sense. The derivative of a position function with respect to time is velocity. Therefore, the velocity center of mass is going to be the derivative of the position of the center of mass. So let's go ahead and follow the derivation of this formula here. Number 1, we start with the formula for the center of mass, which is the sum of all your masses times your positions divided by the sum of M. Capital M represents the sum of all your masses. So start with the center of mass equation with big M representing the total mass of the system. Well, then we're going to differentiate. We're going to take the derivative of both sides. Since 1 over M is a constant, we can pull it out, factor it out. Here you can see the derivative of the center of mass becomes the velocity of the center of mass. The ddt can enter the summation because derivatives of the sum are the same as the sum of the derivatives. So we just pulled that inside the summation symbol. The m's are constant, so they can be factored out of the derivative as well. So we're just pulling the m out. And finally, dx dt is the same as velocity. And what are we looking at here? Mass times velocity. So we're really looking at the sum of our momentum, if you think about it. But that's a very similar equation. Look at how similar the equation looks to what we had before. So the position of the center of mass is the sum of your mass times your positions divided by the sum of your masses, where capital M is the sum of your masses. Here, it's the sum of all your mass times velocities. It's the sum of your momenta divided by the total. Relationship between the center of mass, velocity, and the total momentum of the system. Well, the total momentum of the system is the total mass times the velocity of the center of mass. Basically, we're just multiplying both sides by big M right here, and that is your total momentum right there. Okay, so now let's go ahead and check out the center of mass acceleration. So again, we're going to take the same set of derivatives before. The relationship between the center of mass acceleration and the total force on the system, the sum of all forces, equal to mass times the acceleration of the center of mass. Just as a reminder, an internal force is a force whose reaction force is exerted on another force in the system. Internal forces form action-reaction pairs within the system and thus do not contribute to the acceleration. External forces do contribute to the acceleration. External forces are forces that are considered outside of the recognized system. Center of mass in 2D. Well, when we have center of mass in 2D, we're going to have center of mass coordinates x, cm, and y, cm. We're basically have x, y coordinates of the center of mass. Now, what we basically do is we apply the same equation in both directions. So it's the sum of your mass times positions over the sum of your masses, and the y coordinate's exactly the same thing, but it's the sum of your mass times your y positions divided by the sum of your masses. Let's take a look at these few examples here. In the first example, we have a system of 3 masses. Let's find the coordinate points for the center of mass location. So let's start with xcm. I'm going to call this mass 1, I'm going to call this one mass 2, and this one mass 3. Let's go ahead and find the coordinates for these things because that'll make it easy to plug into our equations. Mass 1 is at -3, 1, 2, 3, up +3. So -3, +3, right? There's x, there's y. And I'm kind of writing the x and y there. Even though I know it's x and y, I'm reminding myself because that's going to help me plug it into the respective equation much easier. Mass 2, I'm going over -4 and down 1, 2, 3, 4. So it's -4, -4 in terms of my x and y. Mass 3 is over 2, down 2. There's my x, y. Okay, so I've got 3 masses. I'll start with mass 1. We're going to go 2 kilograms times the position, the x position of -3 meters. Then I'm going to go on to mass 2. Mass 2 is 5 kilograms times an x position of -4 meters. Then I'm going to go over to mass 3, which is 3 kilograms, and it has an x position of 2 meters. Okay, and we're going to divide all of this by 2 plus 5 plus 3. So we've got negative 6 kilogram meters plus a negative 20. Almost added there, no, multiply. So negative 4 times 5 is negative 20 kilogram meters, and then plus 6 kilogram meters. All of that is over 8 plus 2, or 10 kilograms. Well, the negative 6 cancels with the positive 6, and negative 2 over 2 means the x position of the center of mass is at negative 2 meters. So there's half the answer. Now we're just going to repeat this whole process in the y direction. So the y center of mass is exactly the same masses, but different positions. 2 kilograms times the y position, which would be 3 meters, plus 5 kilograms times negative 4, plus 3 kilograms times negative 2. All divided by the same 10 kilogram mass, 10 kilogram system of masses, that is. That would be 6 plus the negative 20 minus the 6 over 10. And for this, we're going to get negative 2 as well. So the center of mass is at the coordinate points negative 2, negative 2. Okay, there we go. Now, in the second example, we have a system of 3 bars, okay? And the 3 bars are uniform shape, which means the mass is concentrated at the center of those bars. So I'm going to call these respectively, this vertical one here, I'm going to call that bar 1, bar 1. I'm going to call this one here bar 2, bar 2, and that little guy right there I'm going to call bar 3. So if we focused on the center of each of those bars, the center of bar 1 is right here, the center of bar 2 is right there, the center of bar 3 is right there. What I would do now is I would find the coordinate points for those center locations. So the coordinate point for bar 1 looks to be negative 3 up 1. There's your XY coordinate right there. Bar 2 looks to have a coordinate point of negative 1 up 2. Right, there's your XY. And then finally, the third bar down at the bottom seems to have a coordinate point of to the left 2 and down 3. So negative 2, negative 3 would be my x coordinate point there. So let's do our equation. So the x position of the center of mass is going to be now what I'm going to do with this, because I wasn't really given a mass like I was in the other problems. What I'm going to do is I'm going to relate the mass to how long the bar is, since they're all kind of uniform density here. So I'm going to call bars 1 and 2 are 8 units long, so I'm going to call them 8 mass units. So this is 8 mass units, this is 8 mass units, and this is 2 mass units because it's only two lengths long. So we're going to go 8 times negative, let me see, times negative 3. Okay, we're doing bar 1 right here. And then plus 8 times negative 1. And then plus 2 times negative 2. Okay, all of that is over 8 plus 8 plus 2 kilograms. Now all that adds up to, we have what, negative 24 plus negative 8 plus negative 4. Okay, and all that is over, let me see, 18 kilograms. 18 mass units, if you will. So add up all those, you get negative 36 over 8, which is negative 2. So the position is at negative 2. For the y, we're going to do the exact same thing. We have 8 mass units times negative 1 for the first one, or positive 1, excuse me, plus 8 mass units times 2 plus 2 mass units times negative 3. All that's divided by your 8 plus 8 plus 2, or 18 mass units. And we're going to go 8 plus 16 plus a negative 6 over 18. That would be 18 over 18, or 1 meter. So center of mass, in this case, is at the location of negative 2, 1. And in our final example, we've got some areas here, some regular area shapes. We're going to be finding the center of mass of these various rectangular area shapes. Well, we're going to do the exact same thing we did before. We're going to locate the center of the object to be considered where the center of mass of each of these. So if you notice, here's one rectangle here, right there. There's one rectangle here, and there's one rectangle here. So what I'm going to do is I'm going to label these rectangles. I'm going to call the big one 1. I'm going to call this one 2, and then this one 3. Okay, let me use a different color so we can actually see them. 1, 2, 3. Okay. Now we need to identify the center of these rectangles. Well, the center of rectangle 1 is right exactly there. The center of rectangle 2 is right here, and the center of rectangle 3 is right there. Write down what the coordinate points are. Well, the coordinate point for rectangle 1 is up over negative 1 and up 1, 2, 3.5. So it's negative 1, comma 3.5, up 3.5. Rectangle 2 is over 3 down 1. So negative 3, negative 1. And rectangle 2 is over 1, down 1. Okay, now rectangle 1 has 8 columns and 3 rows, so it has 24 mass units. Both rectangles 2 and 3 are 2 columns by 6 rows, or 12 mass units. So M equals 12 mass units for those two. Okay, so let's take a look. The position of the center of mass for the X position of center of mass is going to be, our first one is going to be 24 mass units times the X position of negative 1 plus rectangle 2, we have 12 mass units, times the X position of negative 3 plus rectangle 3, which is 12 mass units, times the X position of 1. All of that is divided by 24 plus 12 plus 12, all of the mass units added. So we have negative 24 plus negative 36 plus 12. And 24 plus 12 plus 12 adds up to 48. So When we add all these up, we also get, that adds up to negative 48. So negative 48 over 48 means the x position of the center of mass is at 1 meter. Okay, the y position of the center of mass, same mass units, 24. This one is going to be times 3.5 in the y direction, plus 12 times negative 1, plus 12 again, times negative 1 again. All divided by the same 48 mass units. Okay, so if we go 24 times 3.5, 24 times 3.5 is 84, plus negative 12, plus negative 12, and that's all divided by 48. Okay, so 84 minus 24 would be 60 over 48, which is, well, let's see, 12 goes into 65 times, 12 goes into 48 4 times, that's 1.25. So 1 1/4, the center of mass for this one is at 1 and then 1 1/4. Okay, so to make a final mark, I'll make a final mark in terms of the position here. So 1, go over 1 and then up 1 1/4. That would be right there. There's x. There's your XY center of mass right there. For this one, it's over 2 up 1, so it would be exactly right there. Right there's your XY center of mass. And then finally, over 2 down 2 right here would be your XY coordinate point for your center of mass. Okay. Center of mass of continuous objects, section 8.2. Consider a rigid continuous object that has a density that varies with position, rho of x. Remember, this symbol right here is rho, and that stands for density. Specifically, this is referred to as linear mass density. To find its center of mass, we're going to split the object into tiny pieces of length dx and mass dm. And you can see that represented in this picture right here. You're going to multiply all the tiny dm's by their positions, just like we would for the center of mass calculation. So xcm is normally the sum of all your masses times the positions divided by the total mass. Well, you're going to add all of your little dm's times all the little x lengths of those little dm's. Going to multiply all those, or we're going to multiply the dm's times their position x's, and then we're going to add up all of those dm's times x's. So you're going to be going dm times x, times x. So dm times that with x, dm times that with that, dm times, and you're going to add them all up, okay? And if they're tiny enough, you're adding up pretty much an infinite number of them. Okay, and so to get the total mass in the denominator, just simply add up all the pieces. And so here's what we get. The equation for this would be x, the integral of x dm. That would be because remember, integration is all about finding the area under something. So the area, if you look here, length times width. dm is the width, or dm is the this part right here, and x is the width. And so if we add them or multiply them together, we get the area of this thing, and that is where the integral represents. And the integration symbol is just a fancy way of summating all of the masses times positions. But these are all your tiny masses times their positions. And this represents the total of the dm, adding up your total dm's. So now multiply and divide both of the integrals by dx. So let me rewrite this right here. We have xcm, we have on the top part here, we're going to go divide, we're going to go x, we're going to multiply and divide by dx. So you have x times dm right here, and what we're going to do is we're going to multiply by dx over dx, and then we're going to divide that by the integral of, and we originally had the integral of all your total dm, and we're going to multiply and divide that by dx over dx. Okay, and here's what we get with that. Well, the ratio of dm, this what I'm going to highlight right here, the ratio of dm over dx right there, that represents the linear mass density rho of x. So we're going to be changing that into that. And so now you can rewrite this as the center of mass is equal to the integral of x times the linear mass density function. Okay, and we're integrating with respect to x over the total density, again with respect to x. Okay, so this is kind of a bit. Let's go ahead and take a look at an example that kind of shows us how to work this. So in this example, consider a rod of length L whose density varies as a function of the position according to the function, the density function, rho of x is equal to a times the square root of x, where x is the distance from the left end of the rod and a is a constant. Find the distance between the left end of the rod and the center of the mass. Okay, so here's where we're going to start. We're going to do this, take this in pieces, okay? Start with the center of mass is equal to the integral of x times the density with respect to x. Okay, and that's all divided by the density, the integral of the density with respect to x. So what we're going to do is we're going to take the top and bottom integrals separately. Just going to do them separately. Okay, and so I'm going to come back to this right here, xcm equals, I'm going to do the integral of that and the integral of that separately, and we're going to come back to filling out the rest of this, okay? So we're going to hold off on this, come back to it. Now, in the second part of this, I'm going to focus on the top integral. The top integral is the integral of x times the density with respect to x, so dx. Okay, so we're going to be integrating this from 0 to L. 0 means the left end of the rod to length L, which is the distance from the left end of the rod. Okay, and x is part of it, and we're simply, x is part of the equation, but we're going to replace the density with the density function right there. So I'm going to replace that with a times the square root of x, and then dx. Okay, so now what we're going to do is I'm going to kind of rearrange this thing. Remember, a is a constant, and constants can be pulled out. So what I'm going to do is I'm going to rewrite this as the integral from 0 to L. I'm going to pull the a out, and I've got x to the first power, that's this right here, times, and I'm going to rewrite that as x to the 1/2 power. Okay, and dx means we're integrating with respect to x. Okay, so now I've got a times the integral from 0 to L of x to the 3/2 dx. Okay, think about your rules of exponents here. If the bases are the same, what do? I add the exponents, don't I? So that's going to be 1 plus 1/2 would be 3/2. Okay, so now I'm going to use my general power rule. So to remind you what general power looks like, the integral of x to the n power is equal to x to the n plus 1 over n plus 1. Then you evaluate that from a to b. Okay, so that's what we're plugging into right now. This is the integral formula we're going to use. So this is going to be a, okay, and if I integrate this, it's going to be ax to the 3/2 plus 1 over 3/2 plus 1, and you're going to evaluate that from 0 to L. I'm going to section this off right here because I'm going to leave some room to evaluate the bottom integral too. So this now becomes a times x to the 5/2, 3/2 plus 1, which is 2/2, is 5/2, over 5/2, that's from 0 to L. When you divide by 5/2, that's the same as multiplying by 2/5. So the top integral is going to be 2/5 a x to the 5/2. And when you evaluate this from 0 to L, it kind of goes like this. It's going to be 2/5 a, and then you're going to go, and we're going to plug in L for x here, and then we're going to plug in 0 for x over here. So it's going to be L to the 5/2 minus 0 to the 5/2, which basically gives you 2/5 a L to the 5/2 power. So that, ladies and gentlemen, is going to be our top integral. That's what we're going to be plugging in right there. In fact, I'll go ahead and do that now. So the top part of the integral is 2/5 AL to the 5/2 power. Now the bottom integral we're going to do over here. Hope I left myself enough room. The bottom integral was the integral from 0 to L of rho dx, just rho dx. Okay, so what that's going to look like is this. We're going to integrate from 0 to L of a times the square root of x dx. Notice what we did. We just substituted that for rho. I'm going to pull the a out front, and I'm going to rewrite this as x to the 1/2 power dx. Now you can go ahead and integrate that using your general power rule here. And this becomes a times x to the 1/2 plus 1 over 1/2 plus 1 from 0 to L, which is going to be a x to the 3/2 over 3/2 from 0 to L. Well, dividing by 3/2 is the same as multiplying by 2/3. We have 2/3 a, and then we're going to be plugging in, we're going to go x to the 3/2 right here. And to evaluate that, you evaluate the L first, right? And then the 0 second. So this would be L to the 3/2 minus 0 to the 3/2. And so we have 2/3, that's obviously 0, 2/3 AL to the 3/2 power is the top integral. Let's put that over here. 2/3 AL to the 3/2 power. Okay, so the position of the center of mass would be, well, first of all, that cancels, and so you're kind of left with, when you divide a fraction by a fraction, you're going to be left with 3/5. That cancels. And then when you subtract those two, 5/2 minus 3/2 is 2/2. 2/2 is the same as 1. So in other words, L to the first power, or just L. So the center of mass is located at 3/5 L, or 60% away from the 60% of the length of the rod. Section 8.4, 8.5, and 8.6. A basic equation for momentum, you might recall, is mass times velocity. So how do we relate net force and momentum? Well, net force is equal to ma, which means net force is equal to m times dv dt. What am I doing? I'm just substituting that for A. Okay, and what is that? Well, if you look carefully, mass times dv would be the derivative of momentum with respect to time. So that is also how we can find the net force, is by deriving the momentum function with respect to time. Or as Yoda put it, may the time derivative of momentum be with you. The equation for the conservation momentum of two objects would be m1. Well, first of all, it's the total momentum before collision, or before separation, before anything happens, equals the total momentum after. Now, we can split it up into mass times velocities by writing it this way. m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime, where the prime notation is notating a final velocity after, whether it's collision or separation, or whether after something happens. The equation for conservation of mass of an entire system, okay, the total initial momentum equals the total final momentum, and that is really just a statement of Newton's third law. The total momentum beforehand equals the total momentum afterhand. Comes into the count with the impulse. The impulse delivered to an object, which is force times time, means that an object delivers a force, applies a force on another object. The second object applies an equal and opposite force on the first object in the same time interval. Therefore, we have equal and opposite delivered impulses, which really is just a statement of Newton's third law. An elastic collision is one in which the kinetic energy also is conserved. No kinetic energy lost. In inelastic collision, you do have kinetic energy lost. Okay. Now, perfect inelastic collision, your objects are going to stick together. An impulse is a change in momentum. It's a force times time. It's a force applied over a time interval. Okay. So the impulse variable is the letter J, and that's equal to a change in momentum. That's what an impulse is, change in momentum. But it's also equal to the force applied over a time interval. Think about what we derived earlier up here. The force, if I multiply both sides by time, and I could actually write this in a slightly different way. So instead of derivatives, I could write it as net force, which I'm just going to write as F, equals m times dv dt. And if I multiply both sides by t, I get force times time equals mass times a change in velocity. Well, mass times the velocity is my momentum. So that's how we get this equation right here, is really from Newton's second law. Now, what does this tell us? That impulse is equal to a change in momentum, which typically we'll write it as mv final minus mv initial. That's the easiest way to write it. Okay, but impulse is also equal to force times time, and thus these are usually equal to each other. In other words, force times time is equal to mv final minus mv initial. So those are the three equations we're going to be using for impulse at various points in time. So how about impulse due to a time varying force? Well, that would be, again, the change in momentum, but it's going to be the integral of the force function with respect to time, from some initial time to some final time. Okay, and so on a graph of force versus time, the impulse is the area between the graph and the axes. Okay, let's take a look at the following example. A bullet of mass m strikes a block of mass 9m at rest on a frictionless track. The bullet embeds itself in the block, and the bullet-block combination travel around a vertical loop of radius r without losing contact with the track. Answer the following in terms of mr and fundamental constants. Well, basically, I don't know if you see this or not, but we have a conservation of momentum problem here with what's called an inelastic collision. Okay, why is this an inelastic collision? Because the bullet embeds itself in the block, right? They stick together. Now, the block itself is going to raise potential energy. Change in height, change in speed, we have conservation of energy as we're going up the loop. So there's two different concepts involved in this. And you also have, if we factor in the forces involved here, you also have centripetal force. Okay, so part A. Determine the minimum speed of the bullet block combination must have at the top of the loop so it does not lose contact with the track. So to not lose contact with the track means this implies that the normal force is 0 at the top. So with that implication, we're doing Newton's second law for uniform circular motion. So in other words, net centripetal force equals mv squared over r. Let's go to the top here. The forces on this block would normally be the weight mg and the normal force, but we're looking for the minimum speed, so the normal force is 0 with that. So I'm not going to count the normal force in this time. I'm only going to be looking at one centripetal force, and that's weight. So I'm going to replace the net centripetal force with mg. So mg equals mv squared over r. Masses cancel. And this, by the way, would be v min. V min, if I multiply both sides by r, v min squared is g times r, which means v min is the square root of gr. Determine the speed that the bullet block combination must have if the block has the speed found at the top of the loop. Okay, now we're using some conservation of energy. Okay, so let's talk about the energy at the top. The energy at the top, you're going to have potential energy, which is mgh. But now keep in mind, h, the height right here, this height is really 2 times the radius, radius plus radius. So this would be m times g times 2r, which we could just write as 2mgr. Okay, there's the potential energy at the top. The kinetic energy is 1/2 mv squared. Now, I'm going to substitute for v squared. V squared is gr. So this is 1/2 times mass times gr, or 1/2 mgr. So the total energy at the top would be 5/2 gr, 2.5. Okay, so we've got that part. The energy at the bottom is only going to be kinetic. The potential energy is zero. It's at the lowest point. But the kinetic energy at the bottom is 1/2, and that's 1/2 mvb squared, v bottom. And that's what we're looking for. We're looking for the speed that you must have after the collision, which is right there at the bottom before it goes up the loop. So we're looking for that. Okay, so now energy initial at the top, at the bottom, equals energy final at the top. Okay, and that would be 1/2 m and what, how much m actually is there? Well, when the bullet embeds itself in the block, m plus 9m is 10m. But realistically, all of your m's are going to cancel anyway, so whether you write them as m or 10m, it's really not going to matter right now. All the masses will cancel. So 1/2 m times vb squared is equal to, now the energy at the top would be the sum of those two. So 2 mgr plus 1/2 mgr, which is, we said earlier, 5/2 mgr. So we have 1/2 mvb squared equals 5/2 mgr. Now what's nice about this is if you multiply both sides by 2, you no longer have fractions. You have mvb squared equals 5 mgr. Masses cancel, square root both sides, and v at the bottom is equal to the square root of 5gr. Okay, determine the speed that the bullet must have before the collision if the bullet block combination has the speed at the top found in part A. This, we are now going to use conservation of momentum for what's called an inelastic collision. So momentum initial equals momentum final. So momentum initial would be just the bullet, so it would be m times v naught, equals the momentum after would be the total mass of 10 m times vb, what we just found right here. Okay, and so we're looking for v naught. Notice m is going to cancel again, and so v naught is going to be 10 times the square root of 5gr. All I did was just substitute this with your answer there. Okay, now for part D, write an expression for the kinetic energy dissipated during the collision. So dissipation just refers to energy lost, right, due to heat. So how much energy is lost and converted into thermal energy. Well, to do that, you find the kinetic energy initial, the kinetic energy final, and you subtract them to figure out how much you lost. So initially, we have 1/2 mv naught squared. That's the initial. The final is going to be 1/2 times the total mass. Now, what the heck is the total mass? The total mass times mvb squared. Okay, which would be what? It would be 1/2 times 10m, right, times, well, what's vb squared? Well, if vb is the square root of 5gr, that means vb squared is just 5gr. Okay, so we can go ahead and Now let's remind ourselves that, okay, in this situation here, V naught is the square, is 10 times the square root of 5gr. So if I square root both sides, V naught squared would be 10, if I square both sides like this, I would be squaring the 10, so it'd be 100 times the, and you get rid of the square root, we'll end up with 5gr. So V naught squared is equal to 100 times 5, or 500 gr. It's kind of important because we need to substitute for that. So my kinetic energy lost or dissipated is going to be my 1/2 times my m times 500 gr minus 1/2 times my 10m times 5 gr. Okay, let's figure this out. 1/2 times 1/2 of that would be 250 mgr. And then we're going 1/2 of 1/2 of 10 is 5 times 5 would be 25 mgr. And so the kinetic energy lost would be 250 minus 25, or 225 mgr. In the next example, we have a cart with mass 1 kilogram moves without friction on a platform with velocity 20 meters per second to the right. The car strikes a ball which has a mass of 5 kilograms initially at rest at the edge of a large table. The table is 30 meters long and 20 meters off the ground. The ball and the cart are only in contact for 0.1 second, and the force that the cart exerts on the ball is given by the function F is equal to 30,000 T minus 300,000 T squared, where F is in newtons and T is in seconds. Part A, what is the impulse applied to the ball? Well, normally impulse can be found by taking the area underneath the force time graph. Problem is, that's not a constant force. It's a parabola, and you're not going to be finding a regular area underneath that curve. So instead, you're going to use the integral of the force function dt. That's how we're going to find the impulse. So the impulse is going to be the integral from A to B. Well, A is the original time to the final time. So from 0 to 0.1 of the force function, which is 30,000, T minus 300,000 T squared, and that's all with respect to time, dt. You're going to be using your polynomial power rule, which would be add 1 to the exponent, right, divided by n plus 1. Evaluate that from A to B. Okay, so now this is going to look like 30,000 T squared over 2, because you're T to the first power, minus 300,000 T cubed over 3, and you're evaluating this from 0 to 0.1. Well, half of this would be 15,000. A third of that would be 100,000. So the impulse would be 15,000 T squared minus 100,000 T cubed from 0 to 0.1. So plugging in our values, this would be, when we plug in 0.1 first, and then we plug in 0 second. Now you plug in 0, you have it's just going to be canceled out. So you're only really going to be plugging in the first part. So we get 15,000 times 0.1 squared minus 100,000 times 0.1 cubed. Okay, that gives us 150 Newton seconds minus 100 Newton seconds, which is equal to 50 Newton seconds. So there's our impulse from A to B. What is the velocity, magnitude of the direction of the ball just after collision? Well, the ball has a positive impulse. So the impulse applied to the ball is positive 50 kilograms meters per second. Remember, you can go between kilograms meters per second and Newton seconds. Those are both the unit of impulse. But why is it positive? Well, the ball is at rest. When the ball is hit, it gains momentum, right? It moves faster. So by gaining momentum, we have a positive impulse. So J is equal to, the impulse is equal to mass times delta V, which is mass times V final minus V initial, where the initial speed was 0, which is just mass times V final. So V final is equal to the impulse divided by the mass, or plus 50 kilograms meters per second, over the 5 kilograms of mass, which means it's going to move 10 meters per second. Since it's positive, it's going to move 10 meters per second to the right. What is the velocity, magnitude, and direction of the cart after collision? Well, you're looking at a collision of equal and opposite forces. Well, it's equal and opposite momenta and equal and opposite impulses as well. So if the ball is gaining impulse, gaining 50 Newton seconds of impulse, that means the cart must be losing the same amount. So the impulse applied to the cart would be negative 50 kilograms meters per second, because the cart's slowing down after collision. So we're going to be using the same equation, but we don't cancel anything. So it's mv final minus mv initial, and we're solving for v final. So to do that, I'm going to add v initial, so j plus mv initial equals mv final, then divide by mass. So v final is your j minus, or j plus mv initial over the mass. So it's going to be negative 50 kilograms meters per second, plus the cart was 1 kilogram and its initial velocity was 20 meters per second. And all that is going to be divided by its mass of 1 kilogram. So we're going negative 50 plus 20 divided by 1, or negative 30 meters per second. Now, the way we could write that in terms of the velocity, magnitude, and direction would be 30 meters per second to the left. There's your direction, there's your magnitude. Okay, the objects they continue after the collision. Each one moves off the edge of the platform down below. What is the distance between the two objects from the point of impact? So basically, here's what's going to happen. The ball is going to fly off the edge of the table that far away from the edge. This cart is going to hit the ball and then bounce backwards at 30 meters per second and go off the edge this way. We want to know the distance. You get the distance from the edge of the table here plus 30. So we want to know the distance from here to here, that big distance right there. Okay, so we basically have two projectile motion problems to solve. Don't forget that the height and thus the falling time are going to be the same for both, because it's dropped from the same height. Recall that the height, right, is equal to 1/2 gt squared for a horizontally launched projectile. To solve for time, you need to multiply by 2, divide by g, and square root. So time is equal to 2 times the h divided by g, which would be 2 times a height of 20 meters divided by g, which is 10. So we have 2 times 20 is 40, divided by 10 is 4, square root of that is 2 seconds. So let's take 2 seconds for both of them to fall. So the cart, we're going to use the equation x equals v naught xt. Well, it's going to go off the edge of the table with 30 meters per second, and it's going to fall for 2 seconds, which means it's going to land 60 meters to the, I should say 60 meters from the left end of the table. So if we go back up to the diagram, it's going to do that, right? And that whole thing right there is 60 meters. Okay, now the ball, we use the same equation, x is equal to v naught xt for a horizontal launch projectile. And the ball goes off at 10 meters per second, falls for the same 2 seconds, which means the ball is going to end up 20 meters from the right of the table. Which means the distance between the two objects, the distance is going to be 60 meters from the left end plus 20 meters from the right end plus the actual length of the table, which is 50 meters, all of which adds up to 130 meters. Section 8.6 and 8.7, elastic collisions. If two objects, M1 and M2, undergo any kind of collision, then the center of mass of the M1-M2 system does not change its motion in any way. It is sometimes easier to analyze a collision by changing our reference frame to that of the center of mass, called the CMRF, or the center of mass reference frame. In this reference frame, the center of mass does not move, either before or after the collision. In the center of mass reference frame of an elastic collision, the two objects leave the collision with the same speed they had approaching the collision. This information can be used to create an easy formula for solving elastic collisions. Consider mass 1 and with initial velocity 1 moving towards mass 2 with velocity 2. If either of those were moving to the left, of course, the velocity would be negative in that sense. So what we have is mass 1, velocity 1, mass 2, velocity 2, and this is the velocity of their center of mass. We're going to transform the center of mass reference frame by subtracting VCM from all the velocities. So if we subtract essentially VCM here, well, that gives you 0, and we're going to subtract VCM from this one and from this one, and so we get this second part. Apply the collision, okay, in the center of mass reference frame. An elastic collision means the object reverses its velocity. So you can see this had a velocity this way, it's going to reverse its velocity. And what that does is it ends up reversing the order in which you are subtracting. Go back to the original reference frame by adding VCM back. Okay, so it's no longer 0 in the middle, it's back here. And what that does is that helps you relate to the velocity of the center of mass to the velocity of each object. So note that the final velocity of both objects is related directly to the initial velocity of the object. And it's related by this relationship of 2 times the velocity of the center of mass minus the initial velocity. You can see that's true in both cases for 1 velocity and for object 2 velocity. Just a shortcut. It's a nice little shortcut. Coefficient of restitution. Well, that is basically the ratio of the final speed to the initial speed. okay, of one of the objects in the collision. Now, through a little bit of a derivation that pretty much is very similar to how we got that right there, the final speed involving the coefficient of restitution would be something similar to 1 plus that coefficient times the, so instead of 2, right, it's 1 plus that coefficient of restitution times the velocity of the center of mass minus, now instead of just VI, it's the coefficient of restitution times VI. So there's a little bit of a derivation involved in that, but that's the formula that results. Okay, so how about collisions in 2 dimensions? Okay, so like a glancing collision, like if you're playing pool, playing billiards, and you can see this ball is about to hit this ball at an angle, and this ball 2, is going to go up at this angle, and ball 1 is going to go down at that angle. That's called a glancing collision. You can see it's moving in the X and Y direction in 2 dimensions. Well, now there's a nice shortcut. If the masses are identical, like in a game of billiards, it's a really nice shortcut that just involves Pythagorean theorem. Okay, and I'll share that shortcut with you in a second. But we're going to talk about and do an example of what happens when they're not, the masses are not equal. So what happens when they're not equal? Well, we basically use our momentum equation. So it's m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. And what we do is we copy this equation twice. Okay, so I'm going to pause the video. Go ahead and pause the video right now. Write the equation twice. Okay, now that you have it written twice, we're going to write x, 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 x behind each term in the first equation. And then we're going to write y, 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 and y after each term in the second equation. So it's basically applying the conservation of momentum equation in both directions. Sounds like twice the work, huh? But actually what you'll find is there's a lot that cancels, so it's actually just as easy as if it were in 1 dimension. Okay, so how about that shortcut? So we have a special case. If 2 masses are equal, then the angle between them is going to be 90 degrees, which means Pythagorean theorem can be used to essentially relate the initial velocity right here to the 2 final velocities here and here. And so the initial velocity squared is equal to the final velocity of one squared plus the final velocity of the other squared. Again, this is only a nice shortcut if the masses are the same. So what if they're not the same? Well, we have an example to try to figure that out. We have an 8-kilogram puck that's moving at 2 meters per second, and it strikes a 2-kilogram puck at rest. So I'm going to call this mass 1, and I'm going to call this mass 2. This would therefore be V1 initial, because it's before collision. This would be V2 final, because it's the final velocity of the second puck after collision. This would be V1 final, which we don't know what it is. Okay. So we want to find the X and Y components of V1 final. Well, one of the things I would probably do to make the problem work for us is we see that you have the hypotenuse there. Find the components. This would be V2 final in the X direction, and this would be V2 final in the Y direction. So in the Y direction, it would be 10 sine 53, and then this one would be 10 cosine 53. Well, 10 cosine 53 is about 6 meters per second that way, and 10 sine 53 is about 8 meters per second that way. So I just wanted to break that down first. Okay, and oh, by the way, V2 initial is 0 because it's not moving. So what we'll do is we're going to break this down into the X direction and the Y direction separately. Okay, so in the X direction, you've got M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final, and all that is in the x direction. Okay, now before you begin, cancel anything that has no momentum. Well, the only thing with no momentum in the x direction is mass 2, so I'm going to cancel that whole momentum right there. Okay, and I'm solving for V1 initial in the x direction. I'm solving for that. Okay, so how do I do that? I need to take this and subtract it over here and then divide by that mass. So I get V1 final in the x direction is going to be equal to M1 V1 initial in the x direction minus M2 V2 final in the x direction divided by your mass 1. Okay, so mass 1 was 8. We're going to go 8 times 2 minus 2 times V2 final in the x direction would be 6. So 2 times 6, and then over mass 1, which was 8. So this is going to be 16 minus 12 over 8, which is 4 over 8, which is 0.5. So V1 final in the x direction would be 0.5 meters per second. Okay, and so now you're going to focus on the y direction. You can just repeat the process, but you're only focused on the y direction velocity now. So M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final, and you just apply a little y direction after each one like that. Now the nice part about the y direction, this is moving in the x direction, so it has no y momentum. This isn't moving, so it also has no y momentum. Both objects have no y momentum. They're only moving in the x direction or not moving at all. So that means this whole equation simplifies to 0 equals M1 V1 final in the y direction plus M2 V2 final in the y direction. I'm solving the equation for this, so I'm going to take this, subtract it over, and divide by that. V1 final in the y direction is negative M2 V2 final in the y direction divided by M1. So M2 V2 final in the y direction, we have negative M2 would be 2 times V2 final in the y direction would be 8 over mass 1, which was 8. Those cancel, leaving you with negative 2. Okay, and all the negative 2, the positive 0.5 just means it's going in the upward direction, or the forward direction. So 0.5, it's going in the forward direction, like this. This is negative 2, which means it's in the downward direction. And if you were to do this squared plus this squared, it would equal that squared. It would help you find V1 final. Now, we weren't asked to do that. We were only asked to find the components, but just sort of talking you through what would be an inevitable connection to this. What is the change in kinetic energy of this system? Well, to do that, you have to find the kinetic energy before and after. So kinetic energy before would be 1/2 mv squared. So it's 1/2 times 8 kilograms. The only thing moving before is puck 1 times its 2 meters per second, and we square it. So 2 squared is 4 times 8 is 32. Take half is 16 joules. Kinetic energy after is 1/2 times m1 v1 plus 1/2 m2 v2 after collision. So it's 1/2 times 8 times, okay, now to find V1 right here, we would be needing to use Pythagorean theorem to find that. So a little Pythagorean theorem up here at the top, V2 final, V1 final, not V2 final. V1 final, which is that speed right there, would be the square root of 0.5 squared plus 2 squared. So we end up with 2 squared is 4, 0.5 squared is 0.25, and 4.25, if you take the square root of that, it's about 2.06 meters per second is V1 final. So 2.06 squared, and then plus 1/2 times 2 times 10 squared. Now 2.06 squared was 4.25, okay, and then half of 8 was 4. So we have 4 times 4.25 plus 100, take half of that, 50 times 10 would be 100. And so 4 times 4.25 is 17, plus 100 would be 117 joules. Now, that's in the after part. So the change in kinetic energy would be 117 joules after minus 16 joules before, or 101 joules. So in other words, this during this collision, there's an increase in kinetic energy of 101 joules. Section 8.8, rocket science. So we have a rocket that's moving, its mass m, moving with speed v, and it's going to expel some gas out of the back end of mass dm. And so let's go ahead and take a look at the different pieces of what's going on with this. If we expel some gas, then what happens is that gas has a small, very small mass to it, so we're going to call the mass of the exhaust dm, which means the mass of the rocket now becomes m minus the dm you expelled. And the velocity of the rocket, therefore, would be v plus dv. So in other words, if you think about it, if you're expelling less mass, or even if you're expelling mass and the rocket's becoming lighter, it's going to move faster. So you expel a certain amount of exhaust, and you're going to be moving a certain amount faster. And to summarize that, a rocket carries rocket fuel that is burned so that the mass dm of the exhaust is ejected from the rocket at a speed vt backwards relative to the rocket, so that an observer, the thrust particles actually move with speed v minus vt. Think about that. The particles themselves, they move with the speed of the rocket, but they're also moving in the opposite direction, okay, that they're being thrusted back, hence v minus vt, and is direction opposite the direction of the rocket wants to accelerate. The result of sending a mass dm backwards at speed vt is that the rocket now has less mass, which would be m minus dm to be exact, and thus has a slightly higher velocity of v plus dv. So in this final example, we have a rocket in open space, has an initial mass of m naught, it's the rocket plus the fuel, and an initial velocity v naught. At time equals 0, the rocket engine is activated. With the engine active and the rocket exhaust fuel at speed vt relative to the rocket itself, and uses fuel mass at rate r. Part A, at some time the rocket's mass has decreased to m. Determine the force on the rocket by the engine propulsion when the engine is active in terms of m, vt, which is the velocity of the thrust that you're throwing the exhaust backwards, and r. R is the rate at which it is the fuel, the rate at which it uses the fuel mass. Okay, so let's start with, we know we're going to be using conservation momentum here, right? Total initial equals total final. So what that tells us is that the momentum of the rocket is the initial momentum, and afterward it's going to be the momentum of the rocket, but it's after thrust, plus the momentum of the thrust. Okay, we can think about it that way. And so from a mathematical point of view, that would be mv equals, this would be m minus dm times v plus dv. It's the small amount of, the rocket is less massive because you're expelling gas backwards and it's going slightly faster. And then plus the thrust would be dm is the mass of the thrust times its backward velocity of v minus vt. Okay, so now what we're going to do is we're going to expand that, okay? Expand that binomial there, and we get mv is equal to, okay, now follow me here because there's a lot of expansion going on with that, those two binomials when you multiply them across. So this would be mv minus vdm plus mdv minus dm dv plus vdm minus vt dm. Whew, that's a mouthful. Okay, so let's see what we did in all this. Well, first of all, we distributed this and this to both. So we FOILed that, okay, expanded that. That is how we get this term here. So m times v, that's the first part. Okay, then m times dv, there's that part. Then there's minus dmv, which is that part right there. And then finally there's dm times dv, which is that part right there. So all of that is expanding that part right there. And then finally what we did is we distributed that to both parts of that binomial, and we get vm times v times dm, which is that distribution right there, and vt times dm, which is that distribution right there. So basically we just expanded this whole thing. Okay, now what we get to do, if you look carefully, a lot of stuff is going to cancel. Don't blink, you're going to miss it. The mv's cancel. And actually this value of dm times dv is also going to go to 0 because it's basically too small. It's a really small mass and a really small differential velocity. It's too small. You'll notice that you have a positive vdm and a negative dvm. Those are going to cancel as well. So a lot of this is going to reduce down, which is quite nice. So we end up with 0 on that side is left over with m dv minus vt dm. Okay, and what I'm going to do at this point is I am going to do a little trick here. I'm going to divide both sides of this. I want to divide everything, actually, even this over here, everything by dt. Okay, you'll see why in a second. I still have 0 on the left side. M dv dt, I'm going to kind of see, we get dm over dt equals, and then this right here is equal to R, and then dv dt right there is equal to A. So just kind of, let me, I don't want to confuse you too much right there. Let me back this up a second. So before we continue, I'm gonna make a quick comment. So dv dt, which would be that part right there, that is equal to A, and dm over dt, that's equal to R. That's the rate of the mass that the fuel rate, the fuel mass rate that you're thrusting out. Okay, so what this kind of boils down to would be ma minus vt times R. But ma is your force. So this would be, if I add this to the other side, your force would just be equal to VTR. Because remember, all I did was substitute force for MA. Part B, write an equation for M, the mass of the rocket after the engine has been active for time t in terms of the given quantities. Well, M, remember the rate is equal to dm over dt. M is going to be the original mass of the rocket, m naught, minus RT, where R is that dm dt, it's the rate of the mass change, and T, that's just times T. It's the time of M of thrust. Part B. The engine shut off at T equals big T, at which point the mass of the rocket is M sub F. Write an expression for delta V, the increase in the velocity of the rocket after the engine completes its burn. Okay, so I'm going to start off with net force equals MA. Okay, but now I'm going to rewrite it as MA equals F. Now I'm going to rewrite this as M dV dt equals, and I'm going to substitute for F, it was equal to R times Vt. Okay, now what I'm going to do is I'm going to divide by M, multiply by dt, and I get dV by itself is equal to R times Vt divided by M times dt. Okay, and then what I'm going to do at this point is I'm going to substitute for M naught minus RT. So this becomes dV equals R Vt dt divided by M naught minus RT. Okay, now what I'm going to do at this point in order to actually solve this differential is I've created a differential equation for velocity as a function of time, is what I've done. But I want to solve that differential equation, I need to take the opposite of a derivative, which is to integrate, and I must integrate both sides. So I'm going to integrate with respect to V on this side, from V naught to V, and then I'm going to integrate this side from from 0 to t, because we'll start at time 0 and time t is going to be the time at which the engine shut off. Okay, now we're integrating the left side, we're integrating 1 dv. Well, the integral of 1 with respect to v is just v, so that part's easy. The second part, the right integral, this is going to take some work, okay? So the left integral is just v. The right integral, we're going to use something known as U-Substitution in order to do that. So here's what it's going to look like. We're going to go the integral of 1 dv from v naught to v And that's going to be equal to the integral from 0 to t of r vt over m naught minus rt with respect to t. Now we're going to use something called U-Substitution. Here's what we're trying to accomplish. We are trying to make this resemble this integral formula here, du divided by u, the integral of du over u. Now, when you get it to look like this, when you get this to look like this integral has a special formula. It's the natural log absolute value of u, evaluated from a to b. Okay, so now we're going to let u be the denominator. Okay, so we're going to let u equal m naught minus rt. Now we have to find du. So to find du, we're going to take the derivative of u. Well, m naught is a constant. Okay, r is a constant. And t is what we're deriving by. So the derivative of m naught minus rt, it's very similar to if you were deriving, let's say, 2 minus 3x with respect to x. The derivative of 2 would be 0, and the derivative of 3x would be 3. Now, if you're doing chain rule, which is what you're doing when you're deriving u with respect to t, let's say I was taking the derivative of this with respect to u, then the derivative of 2 would be 0. The derivative of 3x would be negative 3 du, the derivative of u. So we're going to do the exact same thing. We're going to go, the derivative of m naught would be 0, okay, and then the derivative of negative rt would be negative r, right? But if we derive u with respect to t, it would be dt. We're just chaining that on. Okay, so notice we have an r dt up above. We just don't have the negative. So that's very easy to deal with. By the way, v is a constant, so we can move it out front. All constants can be moved out of the integral. So we're going to do that part. We're going to move the integral over. So I'm going to keep the first part. So we're going from 0, from v naught to v of 1 dv. I'm going to move out the vt, and we're going from 0 to t of r dt over m naught minus rt. But I need to do this. See, my du has to have a negative there. So I can put a negative up there, but the trick is whatever I put on the inside, I have to multiply the outside of the integral by the same amount, because this times itself is equal to 1, and I'm not really changing the value of the integral. It's a little modification. It's a little trick you do to rewrite the integral. So now what I get is this is du. What I'm really looking at is the integral of du over u, which is the absolute value of u. Okay, so this becomes v. The integral of 1 dv is v from v naught to v, and that's equal to, I'm going to erase this part here, and that's equal to the integral of negative vt, which is the outside part, and the integral of that is going to give me the natural log of m naught minus rt, and that's going from 0 to t. Okay, now the calculus is done at this point. Now it's to basically logarithm algebra. Okay, so at this point, let's move this on down here where we have room. And we're first going to evaluate v into v and then v naught in place of v. So this becomes v minus v naught when we evaluate that, equals, and I'm going to factor out that that part right here, and I'm going to then plug in t in for big T in for t, and then 0 in for t. And so I get negative v naught, or negative vt, excuse me, times the natural log of m naught minus r times big T, minus the natural log of m naught minus 0, because I plug in 0 for little t times r is 0, which would just be m naught. So we'll just leave it like that. Now, you remember your rules for logarithms. ln of a minus ln of b is ln of a divided by b. The quotient of the logarithm of a quotient becomes the difference, right, of those logs. So I'm going to go backwards. I've got a difference here. I'm going to write it as a quotient. So this becomes v minus v naught equals negative vt times the natural log of m naught minus rt over m naught. Well, I've got there's my v right there. And what I'm going to do is I'm going to back that step up real quick. Let me back that step up just to make this a little cleaner and a little neater. V minus V naught, by the way, that's my delta V, which I'm looking for. But I'm gonna essentially distribute that negative into both parts right here, and it's gonna reverse the order of the subtraction just to make it a little easier to write. So this would become delta V equals Vt times the natural log of m naught minus the natural log of m naught minus r t. So I wrote delta x for some reason, delta v. So then finally, delta v is going to be equal to vt times the natural log of m naught over m naught minus rt. Pretty tough problem here, so please feel free to pause and rewind as you need to see it again if needed.